Quantum computers are completely new and an entirely different kind of computer. Quantum mechanics refers to the behavior of the most basic parts of our world, the fundamental elementary particles that make up the universe. These elementary particles do not act in the same way the world around us does. They have totally different properties. Sometimes the particles can react in totally unpredictable ways, even popping in and out of existence. If we take these properties out of the quantum world and enlarge them to work in our classical world, we can take advantage of them. Conventional computers work through transistors. A transistor can be in two different states, on or off, 1 or 0. These numbers are known as binary digits, or bits. These transistors react from input. The output goes through logic gates until the final result is outputted and you see what's on your screen. Quantum computers work by taking the properties of quantum mechanics and applying them to computers. Instead of using a transistor to compute data, quantum computers use quantum objects as a special kind of transistor known as a quantum binary digit, or qubit. The quantum object used can be a number of different fundamental particles. The only requirement is that the quantum object behaves in the laws of quantum mechanics. This is the reason why quantum computers are so different compared to classical computers. It computes using the special and strange properties of the quantum world. The first strange property of quantum mechanics is superposition. Superposition is a very odd quantum phenomenon in which an object is in more than one state at once. If you flipped a coin, there are two possible outcomes, heads or tails. Before the coin lands, we don't know if it's going to be heads or tails, so simply, in the quantum world, it would be both. Once it lands and we observe it, it will be one or the other, but before that, it is in multiple states, a superposition. Quantum objects behave in almost the same way as a flipped coin. One of the fundamental particles that can be used as a qubit is an electron. One of the properties of an electron is their spin. The electron isn't really spinning, but rather it describes its rotation along a magnetic field. Think of an electron like a compass needle. The compass will always point north, but if you were to turn it exactly 180 degrees, it would stay like that. Electrons behave in a similar way. Electrons always point in the direction of their magnetic field. That is their sitting position, or spin down. But if you were to turn it exactly 180 degrees, it would have a spin up. This property can be used as a qubit because it can be in a superposition. The difference between coins, compasses, and electrons is coins and compasses aren't quantum objects, and they don't behave in a true quantum way. Real quantum objects change as we observe them. The outcome changes because they are forced to make a decision. Before we measure an electron in a superposition, it hasn't decided whether it's up or down. It has a certain percentage of being both, but because we can't measure something that's in a superposition, we won't know what that percentage is. It's like if you had a coin flat on a table, and when you looked at it, it decided whether it's heads or tails. The real purpose of quantum computers comes in the increase in computing power. With one regular bit, we have two possible states, 0 or 1. When we have two regular bits, there are four possible states, 0, 0, 0, 1, 1, 0, and 1, 1. The computer only outputs one of those variants. When we have two qubits, there are the same possible states, but with superpositions, each qubit can be in a combination of both the 1 and 0 state. This causes quantum computers to be much more powerful than classical computers. This means when you have 2 bits, a classical computer will output 2 bits of information. With 2 qubits, because they can simultaneously be in the 1 and 0 state, it will contain 4 bits of information. Therefore, when more qubits are added, it will output 2 to the power of number of qubits, bits of information. Because of the power of exponentials, this means even a simple quantum computer can be more powerful than our current supercomputers. But there's a big problem using superpositions in computing. While qubits can compute data in multiple states at once, only one of those states can be observed. This means that a quantum computer can compute many different things at once, but only one of those things can be outputted. This means the computer will choose the best variant to output. What superposition allows us to do is have a qubit in multiple states at once. Say you're doing a computation of kicking a soccer ball into a net. Let's say the only variable is the y position on the ball, and it can be 0 centimeters to 100 centimeters. With a regular computer, we would have to do one computation at 0 centimeters, then do another at 1 centimeter, and so on, one at a time. We would have to try the algorithm with every possible position the ball could be in. With a quantum computer, the qubits could exist in every position from 0 to 100. And then, once the quantum computer finds a position where the ball would make it into the net, it would output the position of the ball. A quantum computer can have qubits that exist in every possible state, and then they can output the best answer. Superposition is only one of the many strange properties of quantum mechanics. One of the more bizarre parts of the quantum world is entanglement. Entanglement is a property where two particles behave exactly the opposite. If two particles are entangled, and one is changed in some way, the other will react the exact opposite way. This action of being different than the other particle is done instantly, faster than anything else in the world, even light. It gets even more amazing when you observe the distance that particles can be entangled. Two particles could be on opposite ends of the universe and still become opposite instantly. This property is so strange, Einstein described it as spooky motion at a distance because he couldn't figure out how it worked and even denied it existed. It is really spooky. Objects in our everyday life don't follow these rules. An apple doesn't flip upside down because it doesn't want to be like another apple. Entanglement can be thought of like two coins in superpositions. If the two coins are spinning and the first one lands on heads, you instantly know the second one is going to be tails, even if you don't look at it. The problem with quantum computing lies in engineering one. Quantum computing is all about taking the microscopic world and getting it to control our macroscopic world. The microscopic world is very finicky, it is hard to control, and it is almost impossible to predict. But if we can harness the power of the quantum world, quantum computers will truly change the future, allowing us to do things that would never be possible with classical computers. The strange properties of these specialty computers will open up a whole new world of computing. Quantum computers are very subtle and very complex machines, and we still have a lot to learn about them.